We're streaming.
Yes. I believe we're live. Yeah, cool. Okay. So last time we struggled with equality. Let's see, can I get us to where we were? So yeah. Okay, so we were talking about this equality, type equality, and we wanted to keep it proof relevant. But we proved that in Lean, this proof relevant, in quotes, equality is exactly the same as the proof irrelevant equality, because we could go both ways. So that was disappointing. And we asked questions on the Zulu chat. And yeah, we got basically like the uniqueness of identity. What does the E stand for again? UIE? Is it UIE? No.
UIP.
UIP.
Uniqueness of identity proof.
Okay. Yeah. So that is pervasive. So it kind of infects things. But then later, after the session, we got a link to someone who's done homotopy type theory in Lean. And to do that, you also need an equality or identity. And it looks just like our equality, by the way.
Mm-hmm.
Over here. I'll copy that just to double check. But yeah, it's exactly the same, right?
Yep.
No, it's the same. Okay. But what they do is they have some meta programming to help them. When we go to this project, here they have this hot that you put in front of a theorem. So your homotopy type theory theorem. And then it checks that you do not use large elimination. And if you use large elimination, then my guess is then you end up with something that's proof irrelevant. And if you don't, you end up with something that is proof relevant. But that statement is a guess, educated, uneducated guess, semi-educated guess, semi-educated. All right. So what's interesting here, this theorem is actually quite educational. Not to use that word too much. But basically we have two proofs that A equals B.
Mm-hmm.
And then we want to prove that these proofs are the same. Right, so, but we can't do that.
Just using REFL.
We can do that.
Yes.
If we have large elimination, we cannot do that if we can't. So like let's maybe see this in action, right? So I've imported the library and all of that.
Yes.
So maybe no. I just want to use this file. Okay, so there's the identity imported. So here you can see I cannot do this. Okay, we'll look at the error soon. But let's just see. We don't. If we do maybe T, E. Okay, interesting that both gives an error. Actually, but before that, let's just do our TEQ of this, right? Begin.
Oh, is this that
I think
was that
the,
Lean 3 syntax?
yeah, I think the docs aren't updated.
Yeah, yeah.
TEQ. And then REFL.
REFL.
I'm doing something wrong. Oh, I think, yeah, I don't need semicolons. This is just REFL, right? Yeah, okay. Okay, so that's the theorem. Let's no. So this works when we don't have proof relevance, right? And this all works. And this also works. Okay.
Mm-hmm.
So if we have EQ or TEQ. Okay, now we try it with homotopy type theory, and let's copy this one. Yeah. Okay, and let's try this. Unknown constant id.REFL, yes, because it is id.idp. And what's the error now? Okay, that's not unknown constant idp. Open ID. Is it IDP? IDP.
IDP.
Okay. But I know you can use this. Yeah, okay. So, okay, I can't reproduce it perfectly, but that works, okay? And now if we do the same theory with hot, I expect it to fail. Yeah, so there it says uses large eliminator. So I cannot prove this, right?
Mm-hmm.
Or I need to find a different way to prove it. But
You can't use the
yeah, but we know, so when you don't have homotopy type theory, right, then you're saying you have UIP, right? Which means that, and this implies that there is a unique identity, right?
yeah, unique inhabitant of the equality.
So it means that for all A equals B, A equals B.
Yeah.
Right? And when we don't have this, if you've not UIP, so okay, I think hot implies that you don't have UIP.
Yes.
And that implies that you don't have unique identity. And that implies that this is not necessarily not equal, but they're not
No, there
all.
is. Yeah.
Yeah.
If it has more than one inhabitant, then it
Yeah.
It can have more than one inhabitant.
Yeah. Maybe like maybe like this. So yeah. This can be equal or not equal.
So
that's why this proof doesn't work.
Yeah. So if we link this back to the Agda project, then so the Agda project is not using homotopy type theory, as far as I understand, but it is using this the not UIP part. So it gets the not UIP part from specifying the without K axiom, without axiom K.
Well,
instead.
I think like if you don't have UIP, it does not imply that you have homotopy type theory, but if you have homotopy type theory, you don't have UIP.
Yes.
Yeah.
But in Agda, it's whichever way around it is. So if you don't have axiom K, so axiom K is playing the role of hot for us then. So if you don't have axiom K, then you don't have UIP.
I don't know. It's right, like so. Okay, maybe something with this K rule and J rule that I found that might. So I don't know, but now I'm gonna ramble.
Yeah.
Maybe this is related. But I found this is J. I found something more with J here. All right. So this mentions J, so maybe it's related to the J rule. It looks. Do you still maybe have that link? Where you had the kind of readable J rule.
Yes. Well, I don't have the link, but I can find it.
Yeah, fair enough.
Yeah.
Because that was.
I think I found it already. Let's see.
Oh, okay, cool. I'll stop sharing and then you can.
Yeah.
Okay. This looks very familiar.
So yeah, so if you have without K, so without K implies this we don't have uniqueness of identity proofs because we can't do something like this. So we can't assume that given an inhabitant of X equals X, then we can't pattern match on it with REFL. So that it seems to me anyway that when we have without K, then so it's the K axiom that's giving this uniqueness identity proofs in Agda. And then in Lean, it's this what is it, large elimination.
So okay, yeah, I always get the K and without K the wrong way around. So let me just. So when you have the K rule, you can pattern match on REFL.
Yes.
That means identity is unique.
Yes.
Okay.
That's my understanding.
Yeah. Can I quickly share my screen and we can like
sure.
Also write this down because I found your link.
Oh yeah, so I didn't paste it in the end.
No, but like it was very easy to find, and so I'm just gonna take these, just gonna put them here. Different, probably outdated, but okay. And then so this is the K rule that I just copied from here. Okay. So Agda K rule.
Mm-hmm.
Pattern matching on riffle, which implies UIP.
Yeah, so we can pattern match a equality type just using REFL.
So without K implies not UIP.
Yeah.
I feel like like last week, like, remember how we discussed the not situation and how Agda was better at like inferring these types?
Yep.
It was better at inferring these types because it uses the K rule.
Yes.
Okay, just no.
Exactly. And so
K rule is better at inferring types than the J rule, especially for not proofs, false proofs, in our experience.
yeah.
Because maybe that's not true. Okay. And okay, just want to copy this J rule from Agda. So does without K use the J rule?
So if you have without K, then you get to use the J rule.
Okay. Okay, yeah.
And this is because it's like it's definitionally equal or something. If you get to you specify the right and the left hand side.
Okay, so this is what confuses me. Okay, so without K implies the J rule, right?
I think without K, the J rule is allowed. So it doesn't imply it. It just means that the J rule is accepted. That you can use the J rule. Yeah.
Okay.
So the J rule is compatible without K. If that's not confusing sentence.
No, that's very confusing.
Yeah.
Okay, but J rule is used by Coq, Lean, etc. K rule is only used by Agda. Okay. I just want to add here, like, Coq has proof relevance. Lean has proof irrelevance. Okay. Just trying to collect the facts here because I don't know. I'm still very confused. And then the one other fact here was if you don't have large elimination in Lean, it implies you don't.
Yeah, no, not UIP.
Yeah. Okay.
that's my very hand wavy understanding, is it's this large elimination in Lean which is giving you UIP.
Yeah. Okay. So then. Okay, and we don't know, so large elimination is, I feel like there's some relation with K and J, but I'm not sure.
Mm-hmm.
Okay, but maybe we can just look at these two J rules and see if they relate to the Agda J rules here.
Yeah.
Just to collect another fact. Yeah, I don't know why they're not liking this idea.
Yeah, why can't IDP? Because you opened ID, we can't refer to IDP by. Oh, there's another ID.
No.
Identity monad.
No. Okay.
Yeah.
Fixed. Yeah, easy. Well, I don't understand. Okay. That's annoying. But okay, so this J rule here says so maybe this B is the P. For all X and Y where
So you've got A.
So this J1 is more similar to J prime in Agda.
Ah, good point.
Yeah, nice. Yeah, that looks right. So then there must be another J. It's E. Maybe I missed it.
How many J's? We had J1, J2.
Okay. Maybe that was just coincidence. But again.
Uh-oh, cubicle.
Oh, this doesn't pass type checking. Okay.
Yeah, now we're gone. Very homotopy type theory. I can see the word transport. We can transport identities over paths.
Oh. There we go. Univalence, obviously. Non-computable. Nice. Okay. Maybe. I think this is
Equivalence, I think.
Yeah, so you just need to also import that. This is here. Yeah. All right. Maybe these are the same. Ooh, I don't know.
Well, we got transport. Yeah, so this is like transporting.
Yeah, no.
No, this is something I don't understand. But
yeah, and this equiv is the same as the ISO that we had. So basically, like the functions are inverses of each other. So yeah, I don't think this is related.
No.
But yeah, this is close enough. So, so J1. Come on. Okay. Okay, let's maybe go back to the Zuluk chat.
Yeah.
And just see if there's another fact about these K and J and large elimination there. Okay, so also just I double checked this statement. So
yeah,
if you add the hot prefix to a theorem, then it checks that large elimination is not used, and this way proof relevance is retained. Okay, so not large elimination implies proof relevance. And yeah, this was confirmed.
and I like their username. Documentation
Yes.
fault. Very good.
Yeah, I don't know. It is a good username, but compared to what, yeah, if they understand homotopy type theory, like this is, you know, underselling their skills. Just, yeah. Okay, this was more about computational complexity. I remember. I did not read that fast. I just remember.
UIP doesn't necessarily mean you can't do proof relevant developments in Lean.
No, no.
Because that's what we want, isn't it? We want proof relevance. If we can do it without homotopy type theory, that would be nice.
Yeah.
If you need specifically proof relevant equality, I would switch to Coq or Agda. Lean actually works against you.
Yeah, we could just add that. That's a nice sentence.
Yeah.
Oh, okay. Thank you, Johannes. But yeah, so here's something in type saying X is in this, right? It implies
sigma prime
that there's an I where if you get, it returns some.
So it's proof relevant in the sense that it gives you the method of obtaining the. It doesn't just. It gives you the method of obtaining the gives you the index. It doesn't just say it's in the list. It doesn't just say that X is in X's. It also tells you that which index it is at.
Yeah, it tells you where.
Yeah.
So it's, yeah, so it's almost like it's almost like it's recovering the proof, the relevant part of the proof from the type. And this is,
I mean, haven't we seen this for stuff like is even? You define it is even, and then from the type, from you can you can, something is even, you also get the divisor as well.
Hmm.
So the type doesn't just say it's even or not. You actually, well, I suppose, but there's only one way it can be even, so maybe that's not a good example.
Okay, but this is interesting. Because I was kind of struggling to print the parse that I was trying to do, but I think this shows me exactly how to do it. Well, if you have a language where this regular expression parses this string, then you can match on that, on those types, right? Is that true? Okay, yeah, maybe we can quickly check this, if we can use this technique to recover, because I have the language for us set up in normal and the Homotopy Type Theory version of the language. And I got us, yeah, here's the notation as well. So this is where I was playing. So this A or B represents a language. So that's a character. This is like a regular expression in a very bad notation, right? It's just saying the character A or the character B. That's our regular expression. And then a parse would be parsing a list of, which is our string, with one character A. So we can't eval or print this, right? And it's weird because we're returning a type like this. So I don't know. I don't think we can pattern match on this. Where if we add like an inductive type, which was our language, then we could have, right? Like in this case, you have the inductive type for in. So you can pattern match on it. Is that true? Oh, so we can enter proof mode here and then see, right?
Yeah, that would be interesting.
So this is our thing we want to pattern match on to see the parse. If P what do we want to return? A net.
Crazy autocomplete.
Okay. X for expression. And then we want to destruct X. Cases X.
Lang?
Yeah. But what is lang?
The lang is just this function.
Okay. Okay. Cases with. Make. Okay. Yeah, that's fair. make X is okay, so X is supposed to be our, I don't know, and is the other one.
What?
They both look the same.
So 97 is A, is it? And 98 is B. Is that? Because it's saying
Yeah.
there's 97 and 98. How's your ASCII?
Oh, interesting. This is 97, 97, that's A. 98 is B. And
97. And which MK is this referring to?
char. And this is a list.
Oh yeah, there's the cons. Okay.
Yeah. So
97. So this is A,
oh, sorry.
A, B, and
So
the
this
other
is
one is B, A.
This is the language char for
Yes.
the language char A.
Mhm.
And then we have a list which contains only an A. Below that, we have S, which is our language that is a character B. And our input again is our list that only contains an A.
Ah.
So this is an OR. All right. So this is option A, option B.
Mm.
Actually makes a lot of sense. Okay. So
But now,
let's
what is the type of A? Type of X. Sorry. When we intro it, it's of type lang. No, it's of type.
type.
Yeah. But what is it? Yeah,
Type U.
I see. But what is this MK then? Where is that?
MK is the default constructor, I guess. Yeah, we don't.
A product type. It's prod.mk. I saw it on the when you hovered over it on the
Oh.
left-hand pane. Prod.
Ooh, cool. Nice. Can we do
So
that?
where's prod come from?
Well, I mean, the symbol on line 42 seems like intersection.
Oh yeah.
So maybe it comes
From
from there.
their definition.
Yeah, that's you're right. Should be an OR. And then I think something, yeah, now we get left and right.
Well spotted.
Okay, all right. Wow, so we can it feels almost like I'm doing dynamic typing, right? I don't know, I'm gonna spatter match on this type, and then it suddenly knows, oh, I guess it's inferred, okay. Okay, but so XA. Right, so there we have our character A in our list that only contains A. And this would be the B. So I'm just gonna what's wrong?
Oh, INR. It's got
Oh.
INL, INR in line. Yeah.
All right, cool. Okay, so let's just concentrate on B for now.
Yeah.
But we got the syntax right. Okay, so this is the B. This shouldn't work, right? So what happens? Come on. Doesn't give me a hint. Okay. I guess it shouldn't give me a hint. But maybe this works. Yeah, see. Oh, riffle.
So you need to say exact.
Yeah. Okay, then this should be impossible.
Yes.
Yeah. So what does that mean?
So we have the union symbol.
Like, does that mean like I could just inspect the parse?
Yes. Right.
I want to also say yes, but with confidence, and I cannot.
That's
So-
almost confidence.
No, but I mean, okay. So we defined A union B to be the sum type, right?
Yes.
So then the type of the first argument is, normalized to be of the OR type of the sum type. So then you can pattern match on that as you would normally. If that was a product, you could also pattern match on it as if it was a product.
Yeah.
Because the A character is getting passed all the way down.
Oh, what's interesting here is when we get to the riffles. So when for the sums and products, we have proof relevance, like Jan said. But when we get to the equalities, we've got like we can pattern match and it's unique, but like we don't have we lose information. So so like with OR, we're just making a sum type.
Yeah.
So we keep information. With
Yes.
AND, we'll keep the product, we'll keep information. But like, for example, with concatenation, we have an equality.
But do we care? Do we care about how that equality was constructed?
Yeah, because like yeah, I need to make an example of an ambiguous parse.
Yeah.
And then with yeah, I concat is probably the easiest one. But star makes it so much easier to do something ambiguous. And it also has the equality here. So you care how the string was split, because that tells you like, oh, this is how it was parsed.
But isn't that split encoded in the left-hand side of the sigma type rather than in the equality? So the W's, the WS, the split is encoded here. And the how exactly the joined split thing is equal to the original W, we don't really care. We just care that it is equal. So maybe that's sufficient. As
Yeah,
long as the
and
sigma is relevant, then
then the same here, right?
yes,
With-
we're recording the x and the y. They're in the sigma type, which is
Okay.
relevant.
Okay, that's good. And
That's good news. Well, let's have,
yeah, that is good. And like here, like it can only be equal one way. Like
yes.
so it's fine. Like and here as well. Okay, and that's kind of exactly what's happening here is they're using
Yeah,
the,
because it's being recorded in the sigma type. Is the
yeah.
the thing you want to keep is just in the sigma type,
Hmm.
and the proof is separate.
Hmm. This is good.
Yeah.
Okay. Okay. I'm getting some confidence now. Thanks to
Yeah,
both.
well, I'm happy that
That's
we don't need homotopy type theory. Maybe it seemed like
yeah, yeah,
I was
yeah,
worried
yeah.
that was going to be another 3 years. A pleasant 3 years, yes.
Like the library is pretty good because reflexivity works, rewrite might be working. Like we could have been okay, but this is gonna be nicer. Yeah. Like
But what? So
but now now we can check, do we need TEQ at all? Like yeah, we still need, do we need TEQ?
yeah, that's a good point. If it's the same as EQ, why do we need it?
And also, how does the, like maybe just for a quick tangent before we go down there, like let's just do the pattern matching on the homotopy type theory type.
Yeah.
So we should just be able to copy what we have kind of. This P here.
Is it something like, well, if we use homotopy type theory, then we don't know that two lists are equal in only one way. but we know that. Just it doesn't let us use that knowledge.
Yeah, so here exactly. So
Yeah.
when we get to the XA, we can't do pattern matching on
No.
Raffle. Well, okay, maybe it's the wrong name actually. So it should be IDP. Oh no, okay, it works. Oh,
why does this one work?
okay, well, wait, it should work.
This is good. This is interesting.
It should work. We need HP.
Oh, right.
There we go. Okay. Yeah, so that uses the large eliminator. So then
So is it, instead of saying that there's only one way that two lists can be equal, is it more accurate to say we don't care how they're equal, we just care that they are equal in this case? But for the parsing stuff, we care like when we have the product type, we care, or the sum type, we care whether we went left or right. As for the pass, as the parsing is concerned.
yeah, and with the product type, we care how things were split.
Exactly.
Yeah.
But we don't. We just care that there was an equality for the lists, but we don't have to keep that information hanging around.
Yeah. Okay.
So if you were to do it with the homotopy type theory, what would you have to how would you show that the two lists were equal? You'd have to prove that they are. You have to define a function that goes from one to the other.
You can prove that things are equal.
Yes.
You can't prove that equalities are equal.
Yes.
So there's like a reflexivity tactic. I don't know. What are we doing?
Oh, I see.
No. Oh, well, we can just always do this, right? But we can't.
Yes. But we can't pattern match on the particular. We can pattern match on the equality, I suppose.
Yeah, we can't. Yeah, it doesn't allow us to pattern match on XA.
Ah.
So it's kind of just like if you have false, you can't. The IDE kind of reacts the same way. Just goes like, I don't know what you're trying to do. But yeah, you can still like finish this. No, you can't. What?
Ooh.
We're still using. Okay. Can we do this? Still. Okay. Whoa.
This is funny.
Oh shit.
How are we using the large eliminator here? Const. That dot. Char
Okay.
of that. Decidable less than. It's somehow not happy with
Yeah.
something or other. Yeah. It must be used inside of the A or B.
Yeah. Yeah. Inside of Lang, we're using.
Oh, we are, of course. We are doing equality in there.
Yeah, but we're not destructing it. So.
Okay.
Okay.
We're trying to use magic that's beyond our skill level. Getting burnt.
Yes. So now, can we get away with plain equality?
Yes.
I'm going to call this language prop. We don't need this. This doesn't exist. Okay. So
now Lang has to go to prop.
Yeah.
Try it. And then so we have to change the type of Lang itself.
Oh.
A prop, is it like type U?
Okay. Okay. Okay, just forget about scalar for a second. Let's do an easy one.
A P of W.
Yeah, so this becomes a prop because we're passing. Yeah, so we have a type, and then we pass W to it, so it becomes a prop. And then we want to put the prop in a sum type, but you can't,
Yes.
which takes it back to type. But like, yeah, you can't do that.
Oh, I'm sorry, what did we change?
Yeah, we made all the equalities an EQ instead of a TEQ,
So what is lang?
and we changed lang like this.
Right, but I think lang cannot change. Like lang must be type.
So this is the old one, just.
Right, so can we use type in lang and then somehow
Okay,
wrap the equalities to be types, or I don't know if it's done automatically. If any prop is also a type.
yeah, so we run into this, right?
So what's the problem here?
So this is a prop.
Yeah.
And not a type. So we have
we can make it a type, right?
Sort 0 is prop, right? Sort 1 is type 0. Sort 2 is type 1. So we're saying here, this is, this is a prop. So this is sort 0, and we're trying to return minimum type 0, which is sort 1.
So can we define a wrapper type for this? So what I mean is a type that takes a prop
and returns a type.
Yeah.
Yeah, so that's usually not allowed.
Okay.
But it might be okay since it is a sub-singleton. So let's try something. But I don't know. Lift me up. So mountain. Let's call it mountain. And we'll climb. Okay, we're gonna climb. I just want to try not to overload if there's some hidden lift function. I don't want to get confused. And so this takes a P prop. Oh, well, we need a, maybe this is a type, right? Always need an example for the. No classes.
We got any inductive types anywhere?
Can't believe it. I mean, I'm always using like way too many of these, and now I've got nothing. Are you serious? Okay, here we go. Here we go. Okay, got it. Okay.
Put the
So
name
inductive
and
climb.
then the parameter.
Yeah, this doesn't need to be here. So we want it to be type U, and then up takes a prop and returns climb.
I think okay, so what if you have the prop as an argument to the inductive instead of the constructor? Does it still work?
Let me keep my example around. So here, or do you want it here?
Doesn't matter.
Doesn't matter. Oh.
Oh, have it on the left of the colon so you can give it a name, I guess.
Yeah, I think you're right. I think I need to do that. There we go. Okay. Happy?
No.
Okay.
So climb should have as an argument an x of type P. Does that make sense? Maybe I'm saying something stupid now.
No. Okay. Yes.
Climb P. So term has type.
Oh.
I'm struggling to figure out what this means.
But
I quickly just
no, yeah.
I always want to think like if this was a type.
I don't think we need the P after the colon.
This?
Yeah.
Yeah.
Oh, but then oh.
Yeah.
Mm.
Isn't this okay?
What are the curly braces mean in Lean?
Oh, inferred type.
Okay. But no, I think we want parentheses here. Yeah. Yeah, so then we can just wrap the equality to be a type with this.
Okay, let's see. So here. Yeah. Wow. Okay. Okay. We need a better name. But
No, universe constraint.
Oh.
yeah.
No, don't give up hope yet.
Oh, do we need that? Oh, all is also a prop?
Yeah, we can.
No, all should not be a prop, right? Because you should be able to, well, I don't know. Let's have a look.
I don't think it exists. So I will just.
Oh, it's there. Look, I think deductive all.
Yeah,
right.
I just need to copy it and edit there.
Sorry. Yes.
And then.
Yes. Okay.
P. Yeah. But this is fine.
So
we just don't want to not use equal.
so can we go again to climb?
Yeah.
So oh, it's already polymorphic with respect to the universe level. Okay.
Yeah. But that's this universe.
Mhm.
So we might want to turn it off or on. Just Yeah, we might not want it to be this universe.
So when you say universe U on line 12, it means that whenever you mention U is some concrete U.
Yeah, we're referring to this U.
So then we should make this polymorphic with respect to the universe level.
Yeah, I think here. Let's see what
So
happens.
yeah. So in Agda you would have an implicit universe parameter to the inductive type. I'm not sure if you can do something similar here.
Yeah. I think you do it like this. Too many.
Well, but you need to add it to the definition.
Yeah, let's see. Unused universe parameter. Okay. And then this. Oh no. And that's a, I don't want that error. That's the hard one. Okay, maybe let's just call it something else than you. CU. Okay, so then here. Yeah. Now we can pause it. Yeah, that works.
Yeah.
Wonderful.
But yes, I mean, I'm scared, but like this is amazing. Okay, can we come up with a better name than climb?
Lift. I
No,
don't
just
know.
not lift. Like the only thing we wanted to actually do is lift equalities.
Yeah.
Which is kind of what TEQ was doing. But we're hoping
this might be better because you actually have access to the normal equality.
Yeah, which means we get pattern matching and things for the tactics and rewrites.
Yeah.
But since we're only using it for equality, right?
Mm-hmm.
Yeah, we're only using it for equality.
I mean, you can specialize it for equality.
Yeah, that's what I'm thinking. But like
specialize it for equality and call it TEQ then.
Something like that. Yeah, like is there like a nice way to write this?
P is now well, is P the equality then?
Yeah.
P is of type A equals B or something instead of prop.
Yeah, but that is a prop. A equals B. So like,
yeah. So you would after TU you would have.
If I can do this.
Okay.
Right, and then go.
But these need to be arguments to the inductive type, not to the constructor. And you have a single type because to compare A and B, they must be of the same type.
Yeah.
So you have an implicit type as an argument above. So after TU.
Yeah.
It can be alpha, yeah. And then you have A and B of that type. as explicit arguments in the inductive type as well.
Here.
Yes. A and B of type alpha.
Yeah.
Then we remove the P prop from the signature. And then the argument is A equals B.
You see that, like the
So the argument of up, it takes a single argument of type A equals B. Yeah.
Yes,
Oh,
just
oh.
give it a name. Give it a name.
And this will be climb AB. Yeah. Well, TQ, sorry, TQ. Not climb.
Ah. Woo! So to construct this, you need to pass an equality, which means whenever we destruct this, there will be an equality.
Yeah.
Yeah. Yeah. And this is kind of what we had here.
Maybe we should put A equals B on the right-hand side of the column so we don't have to give it a name, because this X is not used anyway.
Yeah, so in the
Say again?
in line 17.
Yeah, no, line 18.
Oh,
Yeah.
sorry.
You can put the argument of the constructor to the right-hand side of the column. So you don't have to give it a name. Yeah.
I mean,
I like it.
yeah. I don't know what. Okay, we're gonna see if this works. Because
I will get confused by this raffle.
Really?
Yeah.
Then we have some Afrikaans we can use here.
I think we decided last, like this will be trifle.
Raffle. Trifle, yeah.
Or you can make it MK, or right?
No,
No?
no, that's not funny at all.
That's forbidden. Okay.
Yeah.
Yeah, no, I
You
don't
know
know.
the contribution guidelines, Jan, for this.
Sorry.
No, I'm sorry. I think the product constructor is MK for some reason, and I incorrectly said before that that's the default constructor. Like that's the default constructor in a lot of functional languages, but not Lean. In Lean, it's init. So yeah, we could make it init for the unfunny thing that everyone would understand. You know, like the helpful constructor name. I think it's init.
Is it? I thought it was. I'm getting confused now. Maybe I just too many languages, but I thought it was MK. But that's still clicking around the standard library.
Yeah, please. Yeah.
Product. Isn't it that structs? If you define a struct, then you usually call the constructor MK.
Yeah, maybe I'm wrong. See, it's so much easier to be funny than to be right. There's MK as well, like for point.
Yeah, look, I think normally it's by convention it's MK for constructors, but that's just according to David Christensen. What does he know?
Yeah, I know. Okay.
But there's nothing that enforces that. But but yeah, it's short.
Okay, so also this is TU plus 1, right? And this is TU. I think.
Mm.
But let's try it
I'll
out.
take your word for it. Yeah, let's try it.
So right, yeah.
Let's take a chance. Oh, okay. What's the error?
What if you put TQ of, I mean, in the definition, if you don't add +1 to it, does it complain?
No. Okay. And that fixes that. Wow,
Yeah.
you're good. You're good. Okay, this needs no fix now.
No
Okay.
fixes.
Here's climb again.
We may want to have an infix version of that.
Oh, definitely. Okay, that's good. I wonder what the infix version's notation will be.
It will be the emoji, Unicode emoji of a trifle.
No, we've done it before. We've done the notation. It's here. There we go.
Oh,
Yeah, so lame.
trifle emoji.
Okay. Man, I can't believe that just worked. I mean, pretty sure I would have not been able to do this on my own. Like, so thanks. Like that, yeah. This is, yeah, very good definition here. Okay, but we have to test it out. We have to do a little proof.
Oh,
So this should be
you
pretty
need to
quick.
do the pattern matching.
Yeah, just hold on a second. Language notation prop. Prop. This should all be good. And I don't really care if that works. And then we need calculus. Well, yeah. Calculus prop. And we don't need that. Action notation prop. We don't need that. Okay. And cool. Oh, that worked way too fast. All right, so we're at our first proof because we don't need to change anything. And we can't use REFL because we're in TEQ, right? So constructor and then we can use refl. Right, because we just need to destruct, and there's only one constructor for TEQ. So, like, we could work towards an easier way to do this, but I mean, that's very nice
Yeah.
already. Whoa, 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 whoa. So this should also just be constructor. Okay, we don't have these things yet, but okay. This experiment already gives me a lot of confidence. We need something with a rewrite to really like nail it for me. And then
Is it possible to unwrap it and then apply the rewrite?
yeah,
Or
I just need to see like how
ah,
would it be that easy? Like, so maybe just like a rewrite paste. So this should be B equals well, oh, this is what am I doing? Okay. I want some stupid proof that A equals B, right? And then I want to say like A is equal to something and B is equal to something. So let's just rewrite. Because then A is equal to something and B is equal to the same thing. And then
you can do
we rewrite
transitivity.
Sorry?
You can do transitivity. So you can have A equals B and B equals C as arguments and then prove A equals C with a rewrite.
Yeah. Yeah, like this. Yeah. All right. Cool. I don't know why we have that. Okay. What's wrong? Oh, for all. Okay. Okay. Cool. So this is the easy way to do. Okay. That doesn't work.
So can you case on A, B, and BC before doing the rewrite?
Yeah. I was just trying my luck.
Ah, right.
Yeah, maybe it was clever enough.
Yeah, but no. MK, right? That's the
Oh, but there is not a tactic that does that.
yeah, I think
Cases?
not in Lean.
No?
No. Yeah. You can do cases A, B like that.
Yeah.
That did not work. Yeah, see that worked. The equality became this, but when we do this, it just gives us some lang. That's
okay.
very weird. That I don't know why. That's very weird. But if we do this and what? Okay, let's just do rewrite AB. Should be able to do cases B, C with. And now we need to destruct and then
So can you pattern match a pair in Lean as you do in Haskell? So what I mean is, if we want to try to avoid to use two different cases, can we pair AB and BC as a tuple?
okay. Yeah, that's a good question.
No? Okay. Well,
No, but like if we do this, it just if we write code instead of a proof, then we can do match AB, BC with, and now we should be able to do no. Oh, yeah, okay, we don't get tactics, so I can't see. Okay,
Prod AB.
yeah, usually the product symbol is used in the type, not in the term.
yeah,
Okay.
but yeah, that's why I was first trying this.
Says concat. Maybe the comma is not.
So you know what? In no?
Yeah, it's lang.concat. It was defined there.
Yeah, but there's no. There's no AB here. Okay, maybe in the final one. But you're right, like it's a concat, but this is not a concat.
No, it's the comma. The comma is syntax sugar for concat.
Oh. Okay. Okay. Cool. Let's just go to language prop here, where that notation has not been introduced yet. And then we can just do it here. Okay, that works. Okay. And then, yeah, now you can go by, and then they're pattern matched out.
Okay.
Yeah. But let's actually now, your previous question is then still valid. Unanswered. So here, can we do this with a theorem? Yeah, no. Yeah, this just destructs one thing. Yeah, it doesn't handle that syntax. So
Boo.
Can we try with the destruct tactic?
I don't think there is a destruct tactic.
Oh, there is no. Okay.
Yeah, in the cock there is, yeah. But
Okay.
yeah, unknown tactic. Yeah. I think we built one. No. We built one somewhere. Yeah, I can't remember. But yeah. So this is a bit annoying, right?
Yeah.
But I feel like this problem is easier to overcome than any of the others.
Yeah, this is only convenience.
Even if this is the permanent problem, like this is already better than where we were, I think. But I think we have a chance to make it a little bit easier. I want to try this. And this. If we add that here. Not for climb. Okay. Why is that unknown? Looking for that.
Maybe we'll have to make our own tactic that does that. That does the constructor followed by revel.
I don't know. Yeah, like I think that homotopy type theory did that with reflexivity, writing it all out.
Uh-huh.
But can we show that this is the same as this?
So in the original function, the u was set. Does that make a difference?
Try that. If we go here and add a u, no problem. Not the problem. Like I think this was also implied here already.
Okay.
So just to see how far we are apart. Don't need this one anymore. Yeah, they have to be named.
So can you try, so attribute, the second argument of attribute, can it be an expression or it has to be an identifier?
Like this?
So I mean tq.mk and then reffle as an argument in parentheses. Oh, so maybe it has to be an identifier, cannot be an expression. Because the problem with tq.mk is it still expects an argument, right?
Yes. But so does trifle.
That's true. Oh, right. But the type of the argument, we can see that it's different. So maybe that's the problem.
Yeah, but wow, it's so little.
So close.
Okay.
I think I have to go now. I'll join you the next session.
Cool. Yeah, thanks again for coming. Like
Thanks, Jan.
huge,
Yeah. Thank you.
huge
Yes.
progress, I think.
Okay, see you.
You. Bye. Yes, if we give up on this riffle here for a second, maybe we can still get sump.
Yeah. TEQ.
Mm. Oh,
Or does it need something of type A equals A?
oh,
So why we can get that? Can we get that out of the?
oh, wait. So TQ. Yeah, so this should be reflexivity.
Oh, this is REFL then, is it? Instead of A equals A, we give REFL or R. RFL, yeah, that's it.
Okay. Okay. I'm gonna remove that. Huh. Okay, so then we can retry this.
Mm-hmm.
So now, well, when we get here, should be able to say trifle. When we have the C, when our goal is C equals C.
Yeah. Ugh.
By exact.
Yes.
Yes. Okay. No, that's something. I think there's so.
And you can say simp as well.
Yeah, I think.
Yeah.
TEQ.mk. No.
Beep. Not a proposition or definition. A constructor.
Cool.
You can make a definition which just calls the constructor, then add that to the simp.
Yeah, there should be something to just auto unfold. Like,
Yeah.
I had that somewhere. Inline if reduce. Like, no spatialize. Macro inline. Inline. Inline instance. When do you want to inline? What does it mean? Is it just optimization? Is it that type of inlining? Definitely adds more. Okay, so this is how you add a theorem to SUMP.
Uh-huh.
There is, too much complicated stuff in here. List theorems and nothing else. Sorry, I'm scrolling very fast, but I'm just
Yeah, trying to.
I'll stop if there's anything interesting. And, yeah. Just looking, hoping I have some example, but no. I think that's so. Inline is the best I have.
There was no inline.
Maybe. Don't think you can do it before inductive types. Okay. So here's a SUMP at star. SUMP. Okay, so SUMP doesn't unfold these. And we definitely wanted to do that.
Yes.
Right. Because then we can always go SUMP and rewrite. SUMP subsource, go. And we should be like a acceptable place.
We're a bit behind, but the inline and so on attributes are to do with C code output. They just applied to the C code.
Okay, so just purely optimization.
Yeah, it's optimization.
Okay, that's a fair name for it. Yeah. Okay, what other attributes are there?
Yeah.
Okay, maybe this is not the best thing to Google. Maybe this. Does this think? Yeah, this looks like Lean 4. Maybe. We'll see.
Good question. If you, yeah, I don't know the answer to that. Is it like if you end up at LeanProver.github.io, are you on Lean 4 now? Or is it?
I don't know. Here we go. Reducible.
Oh.
Yeah, let's try that. Ooh, nice. And then Some made no progress. Okay. Ah. Yeah, I'm not convinced. Yeah, these are interesting.
Oh, you can give a list. Ask
This
Lee
is
to give you a
cool.
list of all the attributes present to the current environment
Oh, you can.
with the command hash print attributes.
This?
Without the underscore. With the space instead of the underscore.
Ah.
Oh, it doesn't do anything.
Attributes. Yeah. I like that spelled correctly. No. Close. But this is also cool for later. This recursor can be a cool way to do the induction on concat when we have to split, do induction by splitting the string in separate parts, because there you have to define your own induction principle. Oh yeah, here. Okay, so this is lean 3.
That's the check.
That's
is lean 3. Does it contain hash print attributes?
Yeah. Yeah, I'm gonna say lean 4.
It really. Yeah, I'm not sure there is like a reference manual for lean 4. Yet. Work in progress. Yeah, there's not a lot here.
I've seen it somewhere. I think this is already lean. Might already be lean 4.
I think it's lean 3 because it refers to the lean reference manual. Yeah. Oh, for lean 4.
No.
Who knows? We don't know which one is which. Oh, this is LeanProver dash community.
Yeah, I think they updated. I'm gonna.
All right. Let's.
But it is a case. It is a case. Heavy rifle.
Heavy rifle, gosh.
Golfing. Oh. This is a glossary thing.
Yeah.
Yeah. API documentation. Okay. Oh no. There's search. Nope. I mean, there's the super lane thing where I can just prove you can go back and forth, right? Like, equiv-eq, and then just go TQAB A equals B.
Oh. Interactive type. Interactive type prop.
Oh, fair enough. Like, okay. Yeah, also, so questions. Do we have to redefine equiv?
Mm-hmm.
How can we make rewrite easier? Without needing to destruct first.
Well, for that one, if all else fails, we could write a tactic that does that.
Yeah.
But can we do that without it?
Yeah. Right. Tactic. If okay. Yeah, is that the questions I can tackle for next time before? Yeah, I think I like got a bit better understanding of proof relevance.
Yeah, me too.
Um,
Proof relevance and how it's relevant to our project.
yeah, the sigmas are interesting.
Yeah, because we have a healthy dose of proof relevance already. It's just equalities are special.
Yeah. Yeah.
But it can be confusing, I think, if you start thinking about proof relevance and then you think everything's proof irrelevant. It's not the case.
No. Oh.
Oh, this is not happy.
Yeah, it was working.
Maybe that.
There we go. It's fixed.
Phew!
Um,
You just have to summarize the thing and then it suddenly doesn't work.
yeah.
We just see like prop is not type.
Yeah. I think there is something else. Like a sigma type has a type and a prop, right?
Yes.
And if you look at these, this is like a type and a prop.
Yeah.
Like this could just be a prop.
If there's another sigma, yeah, you've got prop sigma, so you could have sigma prime, maybe. Yes.
We want to return a type.
Yeah. So maybe p sigma is the
like maybe it's p
first
sigma.
component, second component.
We can quickly try it actually.
Yeah.
This might be the easiest. Oh, no.
Sigma.
Okay, but maybe just here I'm gonna hack it. Yeah. See, this is a normal equality.
Yeah.
And it's still
holding the information. Yeah.
It's just this all different, and then this needs to be an and.
Yeah.
And then here you lose the proof relevance part, but that doesn't matter because you only want it here.
Exactly.
And then
we can be picky.
Yeah, same over here. So then, yeah, like this a bit of maneuvering. So like let's add that to do try to use this instead of TQ. And then these
The
are
bit that were left is
it's
maybe you could do that instead.
Yeah, like can you do this?
Oh. Well, lang would change, the type would change, wouldn't it? Because you would have a what's it complaining about? Oh, universe constraint.
Oh.
Type moves in the inverse, different universe.
Yes.
Oh. Yeah, because the product type is just like a degenerate sigma type, isn't it? Where the right-hand side doesn't depend on the left-hand side.
Yeah. Oh, so this is just P sigma. It's just this isn't type. This is in prop. Yeah, okay. Also in prop. in sigma, everything is in type. In P
Mhm.
sigma, you can mix. So P sigma is the only tool we have.
Yeah.
And this is just different syntax for P sigma. So yeah, okay.
Yeah.
That's the only one that we can make work.
Mm-hmm.
This might be useful.
Or you can just use it for syntax. Might make things look nicer.
Yeah, like here.
Yeah.
Like maybe. What? This just work. Oh, yeah, okay, obviously.
Yeah, because you're allowed. Maybe it's not a quote mark. Maybe it's a
Yeah.
whatever it is, some Unicode stuff. I don't know.
Oh, no.
Oh,
Yeah, it's a quote.
okay.
Yeah. Okay, that's fine. I'll figure that out. But this is annoying.
Yeah. Maybe that's just the only case now where we have
Well, it's two of these.
two of them.
And so if you have to figure that out, then it's yeah, it's just annoying. Okay, that's enough homework for me. I'll see what I can figure out. Yeah, but yeah, I'm still confused about the K and J but yeah, some things have
Yeah,
not
so the K and the J,
but have
and then
become clearer.
the fact that some of the files in Connell's repo use the K and some don't, which is nice. It's a that's a nice property of Lean then, of Agda then, because you can mix and match when you have this proof relevant equality.
I don't
in
think
Lean you would have to have two different things.
I don't think it affects proof relevance.
The K?
Yeah.
Oh, okay.
But but I'm not sure. But
well, K is the thing that allows you to pattern match on the equality type.
oh yeah. Okay, I'm too tired.
It's okay. We've got that big chart of what implies what somewhere. We should keep that somewhere.
Yeah, no, I'm keeping that. Yeah, like
we can make another cheat sheet to add to the series.
Well, when we figure it out, but until then, maybe a GitHub issue.
It's going to be like a spider diagram of all the different terms and arrows between them.
I think it would be quite helpful.
Yeah.
Yeah, we have to understand it first. Cool. I'm going to stop streaming. That was a good one.
Yeah.
For me.
Goodbye, everybody.
Yeah. Always miss this.